Hey y'all, this is our first lesson of Unit 7. Our lesson is going to cover the cubic and cube root functions, what they look like, how their transformations work, key attributes, domain, range, intercepts, etc. And then also kind of what those transformations do graphically to them. So first thing we need to do is graph our parent function. So our cubic parent function comes from the equation y equals x cubed, or x to the third power. Remember that third power means that we're going to take whatever our x value is and we're going to multiply it by itself 3 times. So I'm going to go ahead and create this table of values with x and y. And I'm going to choose some values that I know will fit onto our graph nicely. So if I were to plug in a -3, -3 to the third power is going to give me a negative 27, because -3 times -3 is +9. And then +9 times another -3 is going to get me a -27. Okay, -2 to the third power is -8. -1 to the third power is -1. 0 cubed is 0. 1 cubed is 1. 2 cubed is 8. And 3 cubed is 27. Now, something of note here, if you're typing this into your calculator, you want to make sure when you type it in, you have -1 to the third power, as opposed to just -1 to the third power. That is not correct. You're not putting your base in parentheses. Along the way, it can cause wrong answers because your calculator doesn't know that you're cubing that whole value. Okay, so if I were to plot these points, obviously that -327 is going to be -3, -27 is way far off the graph. Okay, we're going to just start with -2, -8, -1, -1, 0, 0, 1, 1, and then we have 2, 8. So if we were just to look at those 3 center points, it looks like we're going to have a linear function right here. It looks like it's going to come like this. Okay, but we know it can't because of those other points. So your cubic function is what we referred to as the disco man earlier in the year, because it's going to come up like this and it's going to do a little jig right there. Okay, so if you notice down here, it looks like it's frowning, it's pointed down. Up here, it's more pointed up. Okay, so we call that concave down, concave up. And this point right here is what we call our rotational symmetry point. Meaning if I were to put my finger there and spin the graph, it would land on itself before it got back all the way around. Okay, even more precisely, we could call it the 180-degree rotational symmetry point, meaning I'm going to spin this graph 180 degrees. It's going to look exactly the same as it does right now. We would spin it the other 180 degrees and we would be in a full circle. Okay, and for this particular parent function, that occurs at the origin. Okay, notice that I also have a domain and a range of all real numbers. So the nice part about that is your cubic function is always going to have a domain and a range of all real numbers. Doesn't matter if we transform it, if we flip it, rotate it, it always has a domain of all real numbers. You're going to see the same is true for our cube root function. Okay, so for cube root, I'm going to put some numbers that I know work nicely over here. So we're going to take the cube root of -8, -2, oops, not -2, -1, 0, 1, and 8. Now, if you recall, for square root, we could not take the square root of a negative number because no two numbers multiplied by themselves, or no number multiplied by itself, will give you a negative value. But when we're doing 3, we can get a negative value. For instance, the cube root of -8 is -2, because -2 times -2 is 4. 4 times -2 gets us that -8. So -2 to the third power yields a -8. Okay, cube root of -1 is 1, cube root of 0 is 0, cube root of 1 is 1, and cube root of 8 is 2. So if I were to plot these points on my coordinate grid, I get -8, -2, -1, -1, 0, 0, 1, 1, and 8, 2. Okay, once again, this is going to come in, it's going to do a little jig, and it's going to go that way. So you'll notice just like the cubic function, we start in the lower left, we start in quadrant number 3, and we move in a positive direction up and to the right, and our graph exits in quadrant number 1. So your parent functions will always start low on the left and exit high on the right. So that's one way as you're looking at graphs to see the transformation. Okay, just like our cubic function, we have domain and range of all real numbers. And this one also has a rotational symmetry point about the origin, or at 0, 0. Okay, you might hear that called your point of inflection, because like I was saying, it goes from concave down to concave up, or the cube root function actually goes from concave up to concave down. Okay, so that's your point of inflection. You hear that more so in pre-cal and pre-calculus, but it is good to know different names of things that you already know. Okay, if you know about a rotational symmetry point and someone refers to it as a point of inflection, rather than not knowing what they're talking about, you can relate it to your term rotational symmetry points. Okay, so here are your two parent functions, the cubic and the cube root